Okay, and our last example is this system where we will end up with complex eigenvalues. And so we're going to get eigenvalues in the form of alpha plus or minus beta I. And if we just take the positive eigenvalue, alpha plus beta I, we will be able to come up with two vectors. B1 is 1/2 K1 plus K1 bar. This K1 bar is a complex conjugate. It's a conjugate of K1, where K1 is the eigenvector that corresponds to this eigenvalue that we get. And so if we add K1 to its conjugate, then we're going to get only the real parts. So this is actually also called the real part of K1. You're going to be adding the real parts because the imaginary parts will drop out. And you're going to add the real parts twice and then divide by 2. So this is the same as the real part of the eigenvector. And then here, if you multiply K1 by negative and then add the conjugate, here the real parts will drop out. And you're going to get just the imaginary parts. And that negative will make it negative you're going to get the opposite of twice the imaginary. And if you multiply by I, you're going to get an I squared, which is a -1. It's going to cancel out the negative and divide by 2. It gives you just the imaginary part of that eigenvector. So rather than using these formulas, B1 is 1/2 K1 plus K1 bar, and B2 is I over 2 times negative K1 plus K1 bar, we could just say that B1 is the real part of the eigenvector and B2 is the imaginary part of that eigenvector. Notice that our solutions are a little bit complicated also. You can imagine with imaginary eigenvalues, you end up with sines and cosines. So you have cosine beta t, sine beta t, and the real part, the alpha, gives you the exponential e to the alpha t. But then you've got this real part and this imaginary part multiplied by sines and cosines. For the second solution, that real and imaginary part switch places, and there's also a little negative built in there. So let's go ahead and solve the system. I'll start by writing the system in matrix form. I have x prime is equal to, and my coefficient matrix is 1, -8, 1, -3 times x. So to find lambda, I'm going to solve the determinant a minus lambda I is equal to 0. And a minus lambda I gives me 1 minus lambda and -8 in the first row, and then 1 and -3 minus lambda in the second row. If I take this determinant, I get 1 minus lambda times -3 minus lambda minus -8 . And if I expand this, I'm going to get lambda squared. Here I get a negative lambda and a positive 3 lambda. That's going to give me a positive 2 lambda. minus 3 plus 8 gives me lambda squared plus 2 lambda plus 5, and that's equal to 0. Now, lambda squared plus 2 lambda plus 5 doesn't factor. I'm going to solve this by completing the square. I'm going to start by bringing this 5 over to the right side. Gives me a negative 5. And then with the lambda squared plus 2 lambda, I'm going to complete the square by taking half of 2 and squaring it. Half of 2 is 1. Squaring it gives me a 1. I'm going to add 1 to both sides. Lambda squared plus 2 lambda plus 1 factors into lambda plus 1 squared equals negative 4. Get rid of the square by applying the square root property to both sides. You get plus or minus the square root of negative 4, which gives you plus or minus 2i, and then solve for lambda. We get lambda is negative 1 plus or minus 2i. Okay, now to find the eigenvector, you really only have to find one eigenvector. You don't have to use lambda equals negative 1 plus 2i and lambda equals negative 1 minus 2i. I'm going to use just the plus 2i. And now we want to solve a minus lambda I times k is equal to 0, where a minus lambda I, we're subtracting off negative 1 plus 2i across the diagonal. So I'm actually adding 1 and subtracting 2i. That's going to give me a 1 plus 1 will give me a 2. Subtract off 2i. And here adding 1 gives me a negative 2. And then minus 2i times k equals 0. When I write out these equations, I'm going to get 2 minus 2i times k1 minus 8 times k2 is equal to 0, and 1 k1 plus negative 2 minus 2i times k2 equals 0. This system is going to be dependent, and you could prove that it is by trying to cancel it out. But what I'm going to do, I know that it's going to be dependent, is I'm going to just solve this second equation for k1. When I bring the k2 term over, both of these numbers, the negative 2 and the negative 2i, become positive. And then I'm going to choose my vector k, so that k2 is 1. And then k1 is going to be 2 plus 2i times 1. And so notice that k, I'll bring that over here, can be written as the vector 2, 1 plus the vector 2, 0 times I. So we've got our real part and we have our imaginary part. Okay, so our B1, is this vector 2, 1, and our B2 is this vector 2, 0. Okay, and we get solutions. X1 is, and up here I'm looking at our solutions. X1 is B1 cosine beta t. So I have B1 is the vector 2, 1 cosine beta t, and beta is the imaginary part of our eigenvalue, is 2. Cosine 2t minus b2, which is a vector 2, 0, sine beta t, multiplied by e to the alpha t. Alpha is negative 1. So I get multiplied by e to the negative t. And my second solution is b2 cosine beta t. b2 is this vector 2, 0, cosine 2t plus b1 sine beta t. b1 is a vector 2, 1. I get sine 2t e to the negative t. And our general solution, I'm not going to write it all out, but is c1 x1 plus c2 x2. So put all this together for our general solution.